Hello everyone, welcome to the P1 lecture series. So this lecture is called P108.10, the 10th lecture of this lecture part 108. So in this lecture I'm going to do another problem, okay? One more problem. This problem is much more significant because it has some historical value, right? So historically this is much more important. So everybody knows that when you go around in ships, right? So if you go around in some kind of a sailing ship, okay, like this, a sailing ship with a mast, and this ship like that, okay, on over the water or the oceans with sailing masters, right? So if you go around like that, then you know that there are some weight holding techniques in these things, right? So you have some kind of poles like this, some poles, and where you can put a rope around it and hang a mass, right? Some mass M, and the other guy is holding that mass from the other direction. A person is holding this mass. So this could be some kind of a large amount of kilograms, like 50 or 100 kilograms, right? 100 kilogram mass, but the person only have to give some force which is much smaller, like 1 kilogram force or something like that. So a person who is applying 1 kilogram can hold this mass, okay? That's the essence of this. So if you want to understand that, there is a something like a rope, pole, and a rope is falling around it, and you can hold a mass which is as heavy as like 100 or 1000 kilograms, some mass, f mass, that of mass, and a person can hold it on the other side with some force which is some force of the say boy, right? So in this case, so f of boy is much smaller than f of m, right? So the rest of this weight is balanced by the frictional force within the surface of this rope, this pole, where the rope is rotating around, right? So the friction will hold some of the masses, some of the weight, okay? That's the principle behind it, okay? So what is the physics behind it, right? We need to find out how the force of the B and a force of M, right, the mass and the boy, is related. What is the equation connecting them? Okay, that's what we are going to find out. So to understand that, I have to take a slice of this whole thing, right? So I'm going to take a cross section of this rope pole, and the rope rotating around it, right? So a cross section of that, so that will looks something like this, right? So this is the rope, this is the rope, and the rope is rotating around the pole, right? And the one guy is standing here, and this guy is applying some force, which is the tension on the string, right? The tension in the rope will be equal to some F mass must be equal to tension, right? Tension in that string, so let's call it T mass. And there is a boy holding the weight with some force FB will be equal to the tension in that string, that rope, which will be TB, right? So just like that. Now I need to understand how can I represent these stuff in physically, right? So physically, how can I represent these numbers, right? So that's the most interesting part. So for that, I'm going to take a small section, right? A small section, say this section, and an axis which is the origin, and from that axis some theta angle, right? Some theta angle here, and I'm going to take some small change in theta, right? Small change in theta, theta plus delta theta. So the angle in between is delta theta, right? So the angle in between is delta theta. So that place I'm going to take out, and then find out the tension, the tensional difference in these both places, and then integrate the whole thing to find the tension as a whole, okay? How the force changes, okay? So that's the idea I'm going to do. So for that, for that, what I'm going to do now is that you can also think that like this. So tension, if the tension here is T, right, some T, and then here the tension will be something different, so it will be T of, here it is T of theta, and here it will be T of theta plus delta theta, right? So the tension will change just like that. So our interest is what is the difference, so what is the change in tension, right? So for that, what I'm going to do is that I'm going to assume that, listen carefully now, because this is going to be the hardest part in this problem, right? So this is a bit complicated, but it is not obvious, but it is very complicated, it is a bit complicated. So I'm going to assume 2 points, right? 2 points here, and from this center, these are at right angles. Okay, 2 points, these are right angles. So I'm going to pat down at a tangent line. Okay, just like that, a tangent line, just like that. Okay, and also a tangent line in this line. Okay, sorry about that. So tangent line just like that. Okay, somewhat that. Okay, so that's the idea. So I just assumed s the pulley, and that's the tangent line. So you can clearly see this is the T of the buoy, and this is the T of the mass, which is the tension, right? So these are the tension direction, so each tangent responds to that. Okay, so now the angle here is some delta theta, so this will be the the angle here will be delta theta by 2, right? So this is 90 degrees, this angle is 90 degrees. So now you can clearly see that this angle will be, right, this angle will be 90 minus delta theta by 2, right? So that will be that angle. So that angle we got. Now what I can do is that I'm going to redraw this thing, right? Redraw this same thing in such a way, just like that. I'm going to redraw. Okay, just like that. This is theta by 2. This is 90 minus theta by 2, right? And this is 90. Okay, so you got that, the same thing. And here is our tension. So in the x-axis, you can see, you can take, this is the x-axis. So you can now take this triangle, the new triangle. So this is 90 minus theta by 2, and this is 90 degrees, then this will be theta, right? So that means the angle on the other side, right, other side of this whole line, this angle will be theta as well, right? So that's very simple, right? So it's theta. 90 minus, this is theta by 2, sorry, theta by 2. So this angle will also be theta by 2, right? Because this was 90 minus theta by 2, 90 minus theta by 2, this was 90. So the total will be, the whole thing will be 180 degrees. So 180 degree must be equal to 90 minus theta by 2 plus 90 minus this new angle. Okay, new angle x. So x will be what, theta by 2. Okay, so sorry, plus this x. So x will be theta by 2. So from that, okay, so if x is 3 theta by 2, then the angle on the other side will also be theta by 2. So we got two angles here. Okay, so we have found out two angles. The angle made with the x-axis, right? So the tension makes, right, tension makes an angle theta by 2 with the x-axis. Okay, so here also it will make the same angle using the same principle. Okay, theta by 2, so that will be the angle. Okay, so we got that. So tension now can be resolved into two components: tension of the buoy in the x-axis, tension of the buoy in the y-axis, tension of the mass in the x-axis, tension of the mass in the y-axis. Okay, you can resolve them. So you can just look at it. So if you take that triangle, so the tension triangle, I'm going to draw the tension here. So this is the tension. So it has an x component, say tx, and y component ty, right? This angle is theta by 2, right? So if you take this side, will also be ty, right? So this is tx. So you now can write down that t of this is t of boy. Okay, t of boy, whatever, both components is the same thing, the angle is the same. So now we can say cos what theta by 2 is equal to t of boy in the x direction divided by magnitude of t of boy. So now you can say t of boy in the x direction is t of boy times cos theta by 2. Similarly, t of boy in the y direction is t of boy times sine theta by 2. Okay, okay, we got that. Similarly, if you look at the other side, in the mass case, this case, the case of the mass, like the tension in the case of that mass hanging, so you can find out the same thing, and you get t of mass in the x direction will be equal to t of mass times cos delta theta by 2, right? It is delta theta by 2, right? Okay, I just, okay, change in theta, I just called it delta theta, right? So theta by 2 is delta theta by 2 because we have taken delta theta by 2 in here. Okay, so delta theta by 2 was the angle, I just called it theta by 2 here for easiness. I don't have to repeat it, delta theta, so that's why I just took delta theta by 2. So these are actually delta theta by 2's, right? So delta theta by 2's. Okay, so t of mass in the y direction will be t mass times sine delta theta by 2. Okay, we got that. So we have resolved four components of tension, right? Components of tension of both the mass and the boy who is pulling on the other side. Okay, we have resolved them. Now now let's do the let's do find out what the forces are in the x-axis. So so if you now want to resolve this, okay, let's apply Newton's laws, F equal to ma, right? So that's the easiest thing that we know to apply, right? That's the basic thing we know to apply. So let's do that. So for that, you assume this surface, and there is tension, and there is this angle. So there is tension in the boy, tension of the boy, and then there is tension of the mass, right? So there is a normal force on the surface, and then there is frictional force on the surface, right? Right, friction. Okay, those are the things in here, right? In the x-axis, you can come, you have tx, t boy of x, and tm of x, and the y-axis we have t boy of y and t boy of t mass of y, right? So I'm going to do that right now. I'm going to do that. I'm going to resolve them. I'm going to use the in the x-axis f equal to ma, right? So uh, before that, I have to do one more thing. Okay, I just said earlier that t must be equal to what? So t will be equal to delta t plus theta by, right? So here you remember that t theta and t theta plus delta theta was the consideration here, right? So t theta is the one-sided force, and on the other side we have a delta theta added to the tension. It will be added or subtracted based upon the action of the friction, right? So t theta and theta plus delta theta will be there. So on, so t boy will be some changed tension, so it will be t of theta plus delta theta, and t of the mass will be the original t. For simplicity, I don't want much more complicated tby tdx and all that, so that's why I'm simplifying it right now. So this can be written as t times what, t of theta will be t, right? T of theta will be t because this is the starting point, so plus some delta t, some change in t. Okay, so that's very simple. Okay, so now tb is that, and tm is equal to some t. So now what I can do is that I can just substitute for those values, right? So I'm substituting for those values here. For, so in the x-axis, right, in this equation, I'm going to write down that equation again. So tbx will be tb which is t plus delta t times cos delta theta by 2, right? And tby will be tb, which is again t plus delta t times sine delta theta by 2, right? Okay, and t mx will be t cos theta delta theta by 2, t cos delta theta by 2, and t my will be t sine delta theta by 2. Okay, symbol form, right? So now we got a symbol form that is much more efficient. So now what I can do is that I can find out I can apply now the f equal to ma here. So in the x-axis, okay, in the x-axis what you have is that you have the tbx, right? Tbx and what tbx and tmx, right? And then there is frictional force. So tbx is acting there and tmx is acting there, and then there is frictional force on either sides. So you can write down that tbx plus tmx minus the frictional force must be equal to some ma, right? Okay, simple. So tbx, you can substitute the value for tbx here. So tbx is just t plus delta t cos delta theta by 2. Now one more simple thing. So you have remember that we have done the approximation, small angle approximation. So cos theta for small theta values will be approximately equal to 1, and sine theta for small values of theta will be approximately equal to theta, right? So these are the two things we have done earlier. So I'm going to use the benefit of that here. So in this equation it will become tbx will be t plus delta t times cos small, that is 1, which is tbx, plus tmx will be t cos delta theta by 2, that will also be t, right? So t minus fs must be equal to some ma, right? So I just simplified that. Now what I can do is that, okay, so I'm sorry about one thing. I just forgot to put down the minus sign, right? So tmx will be some minus sign because they are both in the opposite directions, right? So tmx will be in the one in this direction, tbx will be in this direction. So I'm taking this direction as negative. So you get tbx minus what tmx. So that will be a minus sign here. Okay, so t and t cancels out. So you get, if it is in equilibrium, right? This whole thing is holding on itself, right? The mass is not going anywhere, right? You are holding a mass with your hand on the other side, then there is no acceleration. So a is equal to 0. So you can write down that delta t minus fs must be equal to 0, or delta t is equal to fs. Okay, that's very simple. So let's call this equation 1. So we have found out the change in tension will be equal to friction, right? Exact frictional force. Let's call that equation 1. Now let's do the y-axis. So in the y-axis what happens? So in the y-axis you have, right, in the y-axis what you have is the normal force. I'm going to write it down here up somewhere so that it will be easier. So in the y-axis you have the normal force, right? And you have the tb y, tb y, and tmy, right? So you have tby both results to the downwards direction. I'm taking it as positive, that's much easier. uh, Plus tmy plus n, right? So that must be equal to some ma again. So if it is equilibrium, then it will be equal to 0, right? So that will be equal to 0. Now I can substitute for the values of tby and tmy here. So tby will be t plus delta t times sine delta theta. So sine delta theta by 2 is just delta theta by 2. So it will be TB will be TB, which will be T plus delta T times sine delta theta by 2. So it's delta theta by 2 brackets plus T times uh, my, which is T times Tmy is just T times what Tmy is just T times sine delta theta by 2. So that it will be T times delta theta by 2, delta theta by 2. I'm going to, okay, that must plus n must be equal to 0, right? So that's the basic thing. So now you can simplify this equation. You can simplify based on your preference. So you get t uh, t times delta theta by 2 and t times delta theta by 2 twice. So you get 2 times t times delta theta by 2, right? And you get that plus plus you get delta t times delta theta by 2. So you get plus delta t times delta theta by 2, right, plus n is equal to 0. Okay, now that leaves us to the next part, which is the, okay, so this delta t is very small and delta theta is also small, right? If you multiply them both, you will get something very very small. Okay, very small, so that you can ignore that part. So let's assume it's very small, approximately 0. So that's much more easier, and we don't want that minute variation. It compounds for some minute variation. You can cancel 2 and 2. So plus n is equal to 0. Now t times delta theta must be equal to minus n. Okay, so we got that as well. Let's call this equation 2, right? 2. So let me write down equation 1 and equation 2. Okay, I remember that. So equation 1 was delta T was equal to F friction force, and equation 2 was T times delta theta is equal to minus normal force, right? So you now know that delta T, which is equal to friction, will be equal to some frictional constant mu s, static friction, times normal force. So that will be equal to, you can substitute the value of n in here. So you get what mu s minus mu s times t times delta theta, right? So that's what you get. So now you can simplify this. Delta t by delta theta must be equal to minus mu s times t. So now you know that. So what now you can do is that you can limit these values, right? So if limit delta theta tends to 0, an approximation for some small value, then this will become an integral, sorry, this will sorry, this will become what, dt by d theta. So that will be equal to minus mu s times t, right? So now what you can do is that you can now go ahead and simplify this. You can go ahead and simplify this by taking the t's on one side and the minus mu s times d theta on the other, right? So now you can integrate both sides, right? Integrate both sides and you get log within the limit, say t from t of the mass to the t of the holding buoy, right? So what is the tension change, what is the whole tensional change or tension between these two masses, to when you hold the mass to the buoy, right? So that's the actual idea here. And also the theta is ranging from 0 to some big value of theta. Okay, how much curve it goes. So you now got log t within the limit tm to tb must be equal to some minus mu s, okay, mu s times theta, right? Okay, you got that. So now you can write down is log tb minus tm will be tb by tm will be equal to minus mu s times theta. Now again you can simplify this, so you can take exponential on both sides. So tb by tm will be equal to minus mu s times theta. Sorry, sorry. Exponentiate, so it will be minus e raised to minus mu s theta, right? So TB, what the tension the boy is going to feel will be T of the mass times e raised to minus mu s times what, theta. Okay, that will be the tension felt by the boy. So what this equation gives is that as theta increases, the tension of boy will decrease, exponentially decrease, right? So this, what the effect is that you have some function. So the boy is holding the mass from this side. Okay, something better. Okay, this side the boy is holding the mass from that, and there is a rope and the mass is just like that. Okay, so if you hold the mass, the tb will be exponentially decrease, right, compared to tm, right? The mass of this, the tension in that string decrease when you increase the rolling, right, the rotating rope around the pole. If you rotate the rope around the pole more, the tension b will decrease exponentially. Okay, that's what it says. So this is the correct and most suitable and easiest correlation between the tension in these two systems, right? How can you hold the weight? So basically, if you rotate around a pole, a rope is rotated around the pole much more. The more each time you rotate around it, it will exponentially decrease the weight you have to hold, right? So at some point you can hold like 100,000 kilograms, right? 100,000 kilograms or something like that. All you have to do is just rotate the rope around the pole much more times. Like you can exactly calculate the number of times you have to rotate based upon the weight, right? You have to substitute the value of the weight of the rope and the weight of the mass you want to lift, and theta will be can be found out, right? So theta will give you some kind of angle or 2 radian, so you have to divide it by 2 pi to get the angles as well. So it will be in the radians, so you can easily find that out as well. So that's the basic essence of this problem, and that's the result of this problem, and it's very interesting. The physics behind this actual happening we have found out. So I hope you enjoyed this lecture, and for more videos keep watching.